So hi, everyone. Thank you so much for joining me today to celebrate World Oceans Day. Happy World Oceans Day. Like she said, my name is Ashley King. I'm a graduate student at the Virginia Institute of Marine Science studying plastic pollution, and I'm happy to be here with you today talking about plastics in the ocean. So I'll just start here. Now, I promise that I won't be showing sad images like this throughout the talk, but when you hear the term marine debris, this is probably what comes to mind, right? Maybe even a little of this. But an important thing to keep in mind when it comes to plastics in the ocean is that it is far from an isolated situation. Everything comes from somewhere, right? So I'll just start with a little background on plastic production. So before 1950, you had a number of plastic polymers, including PVC, polyethylene, nylon being invented, discovered, and patented. Starting in 1950, you had plastics being industrially manufactured at a large scale, as well as articles like this one. In 1955, Life magazine had a throwaway living article where this family is so happy because they can throw away all of their plastic because disposable items cut down on household chores. Makes life super convenient. After that, a couple of decades later, you have late 1960s, Neil Armstrong goes to the moon, plants a plastic flag there. But also in the late 1960s, early 1970s, you had the advent of the environmental movement. And so you had the first publication on ocean plastics. But throughout this time, you still had more plastic polymers being synthesized, like polypropylene or low-density polyethylene. And then move forward a couple of decades later, late 80s, you had the prohibition of dumping plastics at sea. And just a couple years after that, you had people starting to look into biodegradable plastics as a solution. So people are starting to find out that plastics are an issue, but at the same time, plastics are now playing a key role in society, right? They're everything around us. They're our clothes, our technology, and so they're really key in our society, starting in the 1990s, though, right when we're starting to see what a problem they can be. And then fast forward a couple decades more, 2019, the European Parliament banned single-use plastic, just 64 years after that Life magazine article. Now, that's up till now. This graph goes up to 2015. But let's look into the future. So we are looking to see more than quadrupling of plastics production by 2050. And so let's put that into some perspective. So picture the Empire State Building in New York. Now imagine 1,000 of them side by side. Now combined, this sea of skyscrapers would weigh about 300 million tons. And this is the amount of plastic that is currently being produced every single year. Now, around half of this is single-use plastics, which means it's just used once before it is discarded, with much of that ending up in our oceans. Now, quadruple that. And that's what we're looking towards in the coming decades. So I want you to think about all the things you throw away. Single-use plastics, including water bottles, toothbrushes, razors, trash bags, cigarette butts, old furniture and clothes, shoes, old phones and CDs, DVDs, VHSs, if anyone has those anymore. As technology moves forward, we throw away the old, right? We live in a convenience-driven society, but this convenience comes at a cost that most of us are lucky enough to not see. But everything goes somewhere, right? Now, a lot of us just aren't aware of the connectedness of the things around us. For instance, storm drains. In this comic, this man is sweeping trash into the drain so that it's out of sight, out of mind. He never sees it again. He never has to deal with it again. But those ducks downstream will have to deal with it. And so at VIMS, we have signs next to all the drains that say no dumping drains to bay, with a little crab on it, just as a reminder to be mindful of those downstream. Now, those aren't next to all storm drains, but I hope that in the future, when you come across a storm drain, you just picture that little crab standing right next to it. But let's back up and consider mismanaged waste, which is that which ends up in the environment unintentionally. And eventually, as the saying goes, all roads lead to the ocean. So this can be by way of garbage overflow, like the image on the left, where that trash is no longer fits in the trash bin, and so one good sweep of wind and some of that trash goes into the ocean, which is just walking distance away. Or mismanaged waste can happen by debris being lost in transit. For example, the cargo ship on the right, that's in a bit of a precarious position at the moment. And funny enough, several years ago, there was a cargo ship like this one that had thousands of rubber duckies on board that were accidentally released. And so they managed to find a perk of that plastic pollution by using those rubber duckies to study ocean surface circulation, but still not a good thing. Now, mismanaged waste can also happen by having no or very rudimentary waste management to begin with. Now, so in this figure, countries that are darker colored have a larger amount of plastic waste that is available to enter the ocean. As you can see, much of the globe contributes to this issue, but that Southeast Asia struggles with this especially. Shown another way, this table lists by country the amount of plastic waste that is generated by population and the percent of that which is mismanaged. And as you can see, at the top of this table, several countries are from Southeast Asia, with up to almost 90% of waste in some cases being mismanaged. While here in the United States, we are at the bottom of this table with just 2% being mismanaged. But it's important to note that per person, we in the United States are the absolute worst at generating plastic waste, almost double the next highest country. Now, this story gets even more complex when you take into consideration the export of trash. The United States and some European countries exports a lot of our trash and recyclables, more than 1 million tons from the US in 2018, which was about 1/3 of our recycling. Exports that to Southeast Asia, among other places. In fact, just recently, China stopped accepting other countries' trash and recyclables. They've had enough. So add all this up, and what is important to us right here is that we in the United States produce the most trash per person and export most of that to countries with poor waste management. In fact, 78% of our exports in 2018 went to countries with poor waste management, thus leading to our trash being released into the environment just in another country. Now, once in the ocean, trash tends to collect in ocean circulation zones called gyres. And here you can see these areas in the North and South Pacific and Atlantic Oceans, as well as in the Indian Ocean, where the abundance of marine debris is much higher than in other areas of the ocean. Now, trash can escape these gyres, though, and can end up back on our shorelines nearby. But these too will probably eventually end up back in the ocean. And you'll have some of this cyclical nature, where it's trapped in gyre for a while, it'll escape, end up on a shoreline, and then end up back in the ocean. Now, one thing I want to get straight really quick is that the Great Pacific Garbage Patch, which is circled here in red, is not what you may have read. So you've probably seen news articles like these claiming that the Great Pacific Garbage Patch is an island of trash that you can walk on that's more than twice the size of Texas. But this is a myth. What the Great Pacific Garbage Patch is a collection of trash, but what it's made up most of is the plastic debris that is the most abundant, which are these tiny plastic particles called microplastics. Now you can see on the left is an image of a sample taken from pulling a plankton net through the surface of the ocean in the garbage patch. And in addition to some larger debris, the majority of what they picked up were these particles that can barely be distinguished. So microplastics are generally defined as plastic particles that are less than 5 millimeters in diameter. And for reference, that's about the size of an old school pencil eraser. Now, microplastics may be intentionally manufactured, for example, abrasives and personal care products called microbeads, or they may be derived from larger plastic products or debris formed through fragmentation due to weathering. For example, fibers derived from washing clothing, or this plastic bottle that is fragmenting. Now, as time goes on, plastic products break down into increasingly smaller and smaller pieces of plastic, some examples of which you can see in the images on the bottom right. Now, microplastics are globally distributed, being found from remote deep oceanic trenches. This is an image of a plastic bag in the Mariana Trench, which is about 7,000 feet deeper than Mount Everest is tall. Microplastics are also found in mountaintops and polar regions, as well as in rain and snow. They've also been detected in the digestive tracts and respiratory organs of numerous organisms, like, for instance, the image that I showed you at the beginning of this presentation, which was an albatross whose stomach was full of microplastics and who had died as a result of it. Now, just like larger plastic products travel, so do microplastics. And as you can see in this figure here, microplastic travel includes a lot of land-based sources, as well as at-sea pollution. A really good example of which is the current situation off the coast of Sri Lanka, where a cargo ship carrying tons, literally, of chemicals and plastic pellets called nurdles caught fire and is currently sinking, releasing those chemicals and plastic nurdles into the surrounding water. This is an image of a cleanup worker wading through the plastic nurdles that have been washing ashore, as well as a couple images of the organisms in the surrounding area interacting with those released plastic nurdles, including a dead fish that has washed ashore. But going back to microplastics transport, these particles are smaller than larger products, so they have the movement pathways and impacts that differ from those larger particles. An example of this is that atmospheric transport plays a role with microplastics. There's a lot more work to be done in this area, but microplastics have been shown to travel upwards of thousands of miles through the air. And their presence in the atmosphere is why microplastics have been shown to be in rain and snow, like I had mentioned in the last slide. Now, one of the biggest things that complicates the situation is that plastics themselves are complex. For one, they contain a mixture of chemical additives. Now, these additives, as the name suggests, are chemicals that are added to the polymer backbone of a plastic product to help the product serve its purpose better. Now, these chemical additives modify properties like flexibility, for example. As you can see here, PVC, the same polymer that is commonly used for piping, can be used as a shower curtain liner when it contains more than 30% by weight of plasticizer additive, which makes it a lot more flexible. Additives can also modify color, as well as resistance to degradation, as well as flame retardancy. Baby clothes, for instance, have huge amounts of flame retardant additives in them because obviously babies catching on fire is not a good thing. But on the other side of the coin is that some of these chemical additives that are used in such high amounts on our products can actually be harmful. An example of this is a chemical additive that is found in plastic products like food packaging, as well as clothes and carpeting, that has received widespread attention recently, which is per and polyfluoral alkyl substances, or PFAS. Now, what makes PFAS chemicals especially unique and concerning to environmental scientists is the forever chemical status, meaning that it is extremely persistent and doesn't break down in the environment. PFAS chemicals have been linked to a number of toxicity endpoints in humans, let alone in the environment, including cancers and immune and nervous system issues, to just name a couple. Now, additives may escape the polymer during physical and chemical degradation of the plastic product or by leaching, which predominantly occurs at the plastic surface. So let's say that this square is a plastic and that it is full of some chemical additive. As I said, that additive can be released by leaching from the plastic surface, which then depletes the surface of the plastic of the additive. And this means that for more of the additive to leach out, it will have to travel further to leave the plastic to be released. But imagine that the particle has now fragmented into four, just like this water bottle. And as plastic debris fragments, its surface area increases exponentially, providing enhanced opportunity for the release of these chemical additives at all of the newly exposed surfaces. A plastic bottle, for example, will have a surface area thousands of times greater than its original surface area after years of degradation. Another thing that makes plastics so complex is that when they are in the environment, they collect things. And one of the things that plastics collect is microorganisms. So just as the boat you see here, or any other object that spends time in the ocean collects organisms, so does plastic. And these biological assemblages always start small, with microorganisms like you can see here. And these diverse collections of microorganisms can include diatoms and cyanobacteria, including harmful algal blooming, forming algae, as well as potentially harmful things like Vibrio and other pathogens. Now, the surface of plastic debris that these organisms call their home is called the plastosphere. And the formation of this plastosphere contributes to plastic movement in the environment because floating debris loses buoyancy, so its ability to float, as organisms collect on the surface. Microplastics, in addition to collecting biological things, they can also collect chemicals from the environment. So here you can see an image of the surface of an unweathered polyethylene microplastic. It's very smooth, so it just looks like a dark gray box for right now, but you'll see how it changes in a minute. Also shown is the chemical spectra of the particle, which is a tool that's used to identify the chemical makeup. And here the chemical makeup appears very simple, just a couple of peaks, which means that there are just a couple of chemicals that were detected, including carbon, which is the backbone of plastic. Now compare that to the polyethylene particle after it has been in the environment for a while. You can see that the surface has become rough and cracked. As I mentioned, fragmentation happens to plastics in the environment. And the chemical makeup has become more complicated. There are more peaks as the microplastic picks up things from the environment. So plastic surfaces collect contaminants, including organic pollutants, and these can include those associated with fossil fuels, like PAHs, as well as legacy industrial and agricultural chemicals like PCBs and DDT. So plastic is a magnet for these contaminants, so the concentration of chemicals that accumulate on the plastics can be up to 100,000 times higher than the concentration of the chemicals in the water. Additionally, heavy metals accumulate here as well, and examples of which include mercury, cadmium, arsenic, chromium, and lead, among others. And this essentially makes microplastics potential chemical bombs for those that interact with them. So let's put all that together. So I'll invite you to my tiny imaginary ocean, admittedly with only 2 fish, but stick with me. So in this ocean, we have microplastics. In this case, the different colors represent different polymer backbones, for example, PVC or polystyrene. And they're all in the same shape in this case, whereas in the environment, plastics can be very differently shaped. They can be fragments or fibers, films, jagged or smooth. And we also have their associated chemical additives. Now in the environment, these additives can leach out of the plastic into the surrounding water, potentially exposing our fish to the released chemicals. Finally, we have our contaminants and biofilms that have collected on the plastic surfaces. Now, if one of our fish or another organism in the environment ingests a microplastic, it is exposed not only to the microplastic, which on its own may be harmful, but also to the chemical additives, the potentially toxic contaminants, and the microorganisms in the biofilm as well. And a big question is whether these microplastics, what every piece of plastic debris in the ocean will eventually become, whether these are toxic. So I'm showing this slide once again just to illustrate that we know that large plastic debris can be harmful when organisms like this turtle, for instance, are caught in them, which makes it harder for them to move around, to catch prey, to reproduce, or it can cut into their skin, making them more susceptible to infection or disease. And we also know that plastics, even microplastics, when ingested, can damage the internal organs of an organism like this bird, or they simply may fill an organism so that they, 1, don't feel hungry, so they end up starving even though their stomachs are full because plastics don't provide any nutrition, or 2, because they can't pass large pieces, so their systems end up shutting down. But since microplastics are so much more complex and can interact with different areas of the ecosystem and different parts of an individual organism, the possible impacts are different as well. And this is illustrated really well here. So as you can see, the various plastic sizes ranging from megaplastics down to microplastics and down to even nanoplastics have the ability to impact different size classes of organisms. So these impacts can range from affecting large whales down to smaller fish and down to microscopic organisms like plankton. Which leads me into going a bit into the research that I, Meredith Evans-Seeley, my fellow VIMS graduate student, and our research advisor and VIMS professor, Rob Hale, are doing to understand microplastic impact in various environments. So my research at VIMS is more focused on the terrestrial side of things, but remember, everything runs down to the ocean. So wastewater treatment plants. They receive all the things that go down the sink, down the toilet, discharges from industries and hospitals, and in some cases, stormwater runoff off the streets. And any microplastics inside the home environment, including fibers from clothes and carpets, floor dust and microbeads and personal care products, as well as tire dust and other particles from outdoors, in the case of a wastewater treatment plant receiving discharges from both indoors and outdoors, all of that will end up in wastewater treatment plants. So because of this, wastewater treatment plants are a major collection point of microplastics. There, upwards of 90% of the microplastics are removed from the effluent. And this means that if, say, 20 microplastic particles enter a wastewater treatment plant, 10%, or just 2 particles in this case, will end up in the effluent, which is released into a nearby water body. And a lot of the rest of the particles, up to 18 in this case, will end up in the sludge. So the purpose of wastewater treatment plants is basically to remove crud from the water that is released into effluent. And that crud becomes sludge. And the sludge is full of nutrients, so it is commonly put in agriculture as fertilizer. But also in the sludge is the microplastics that accumulate there. So when the sludge is land applied, it may inadvertently transfer additional contaminants like microplastics and their chemical additives to the soil. So we are researching how microplastics and their chemical additives are changed during the complex treatment processes they're exposed to during treatment, and if the additives leach out during processing and or after treatment and once it has been put into the environment. Some work that Meredith has done is related to bacteria and sediments. Now, just like how you and I ingest food, like this piece of pizza, and the bacteria in our stomachs help to break down that food so that we can get the nutrients from it, which is a delicate balance, as all of us know. The ocean has the same delicate balance, where bacteria in the sediments break down organic matter, like this dead zooplankton or some feces, or some microplastics that have sunk down to the bottom to provide nutrients for the plants. And so this delicate balance is mostly governed by the nitrogen cycle. In this cycle, nitrification increases the available nutrients for plants, and denitrification removes the nutrients available for the plants. And Meredith researched how microplastics could disrupt this delicate balance. So she found that different microplastic polymers, for example, PVC or polyethylene, had different impacts on nitrogen cycling. Some had no significant impact, others increased the available nutrients, and others decreased the available nutrients. And this is important because these processes are very important to plants and microorganisms around the world. And microplastics disrupting these processes definitely is important to understand. But this was the first study of its kind, so larger repercussions of this are still in need of much more study. Some of Meredith's current work is investigating how microplastics interact with disease in fish. So fish exposed to this virus in the ocean may result in some mortality. As you can see, one in 4 of these fish has died. But the environment is complicated, right? You're never exposed to just one thing. And so when fish are exposed to the virus in addition to some microplastics, does that result in an increase or decrease in fish mortality? And results are coming soon on that, so wait for a publication from Meredith. And finally, some work that a high school student, Virginia is actually now a college student, but when she worked with us, she was in high school, did in our lab a couple of years ago. Now, one of the important things about microplastics is that they're small enough to be ingested by or to interact with the smallest of organisms in the ocean, which are those that make up the base of the oceanic food chain. So that makes them very important. So this is an image that Virginia took of polyurethane microplastics, these little pink things being ingested by this organism, which is a brine shrimp. Now, the microplastics were egested, meaning they were pooped out, within 48 hours or 2 days after exposure was stopped. But in those 2 days that those microplastics were in the brine shrimp, some additives likely leached out into the organism. So when people think about plastics, they don't tend to think of them being associated with or contributing to climate change, but every step in the plastics life cycle contributes. Let's walk through it together. So the beginning of the plastics life cycle begins with oil and gas development. Oil, gas, and coal are the fossil fuel building blocks of plastics. And today, up to 8% of annual global oil consumption is associated with plastics. And if the reliance on plastics persists, and indeed it is slated to increase by a lot, plastics will account for about 20% of oil consumption by 2050, and that number is likely an underestimate. Additionally, plastics refining and manufacture produces greenhouse gases, which contributes to climate change. And the incineration of plastics, as is done rather than landfilling or recycling, has a very large impact on emissions as well. In addition to reducing surrounding air quality due to potentially toxic chemicals being released into the air, incineration also releases greenhouse gases. Now, US emissions from plastics incineration in 2015 were 5.9 million metric tons of carbon dioxide equivalent. And based on projections, if plastics production and incineration increase as expected, greenhouse gas emissions will increase tenfold by 2030 and 20-fold by 2050. Finally, even as plastics sit in the environment and fragment into microplastics, they emit powerful greenhouse gases like methane and ethylene. And similar to what I discussed as additives leach out with more surface area being exposed, so are these gases released. And it actually turns out the plastic that gives off the most greenhouse gases, which is low-density polyethylene, which is used to make plastic bags, is also the most prevalent of discarded plastics in the oceans today. So we've discussed a lot about plastics in the ocean, but one of the questions that we get asked the most is, so what can we do about it? How can we combat a problem that impacts the environment in so many ways? And I want to stress that governments and companies and industries carry a lot of responsibility here, as this is a pervasive global issue that will require global cooperation, like that of the Paris Climate Agreement, for instance. And additionally, a recent study found that 100 companies were responsible for the production of more than 90% of all plastic waste, with only 20 of those companies being responsible for 55% of the world's trashed single-use plastic. But as far as solutions, we need to think of the plastic debris problem as an overflowing bathtub. So if your bathtub is overflowing, is the first thing that you do start to clean up the water on the floor or to turn off the tap? You turn off the tap. Same goes for plastic. We need to stop the release of plastics into the environment. And cleaning up debris that are already there is important, definitely, but first things first, and we need to prioritize allocation of funds and effort here. Which is shown really well with this figure. This is from a publication in 2015 that laid out steps to solving the plastics issue. And as you can see, step number 1 is to reduce plastic production. And moving on from there is to look into innovative materials and adjusting our waste generation and waste management. And then moving on to picking up what's already there in the litter capture. But we're still all the way back here. So for individual actions that you can do though, you've probably heard the saying, reduce, reuse, recycle. And another R word has been added to that, which is refuse. The first thing that we can do is refuse plastic products as much as we can. An example of this is that here, rather than using the single-use plastics in a situation like on the left, I carry around a reusable utensil set like this one that I can wash and reuse. Also, solutions like the paper straw on the right have been emerging. And so refuse as much as you can, reduce when you can't refuse, reuse what you already have, and the next step is recycling. So only about 9% of plastics globally are recycled. So this isn't a sustainable solution currently for the continued production of plastics. And one important thing to know about recycling is that just because you see these chasing arrows on a product does not mean that it's recyclable. So the numbers inside the recycle triangles each represent a different plastic polymer. For instance, number one is the polymer polyethylene terephthalate, or PET, which is commonly used for water and pop bottles. And it's important to know what the recycling requirements are in your area. For instance, in my area, and in some of yours too, but I encourage you to go look, I can recycle numbers 1 and 2, but only if they have necks, like the neck of a water bottle. So I try to avoid buying any plastic products that I can't recycle. Now, what you can and can't recycle is the policy of the people who collect or accept your trash or recyclables. So find out the rules in your area by contacting the company if you can to see what they accept, or if they have a website, go there. In fact, that's how I know the rules that I need to follow, because my recycling facility, the Tuning Convenience Center, has info on the website. A great example of how complicated recycling is the image here from the Seattle Public Utilities, where the cap of the tallest bottle can be recycled, but only if it's kept with the bottle. The bottle itself can be recycled, but only if it's empty, clean, and dry. The middle height bottle cannot be recycled because it is soft plastic. And the smallest bottle also can't be recycled because of its size. Even with all these complications, though, all of these items have the same recycling number, number 2. And another caution about recycling, there's a trend these days to do what is called wish cycling. And this is where you're not really sure whether something is recyclable, but you figure just in case, let's throw it in the recycle bin. And I used to do this too. It's a really hard habit to stop, but it can actually be harmful, because even if the stuff that you have put into the recycling is clean, it is considered contamination if it's not able to be recycled. And if there is enough that is not actually recyclable in a batch, it will all be thrown out. None of it will be recycled, and everything will likely be landfilled. So this is another reason to be aware of the recycling rules in your area, and to unfortunately follow the motto, when in doubt, throw it out, but to reduce your doubt as much as you can by knowing the recycling rules in your area. Some other solutions that some companies like Blue Landing Clean Cult have been coming out with are these reusable cleaning kits. So you keep the bottle, and they send you either a pellet to mix with water or a milk carton with some powder to mix with water to make your cleaning products. Another innovation is these technologies to reduce the amount of microplastic fibers that come off of our clothes during washing, which end up going to a wastewater treatment plant and likely are discharged to the environment. So all the way on the left, you have a filter that filters the water coming out of your washing machine, so that the microfibers, that come out are reduced. The Guppy Friend is an actual bag that you put your clothes in, that you put the entire thing in the washing machine. And same with the Cora Ball, you put it in your washing machine and it collects the microplastics that are coming off of your clothes while they're being washed. Now, I bet everyone in this room has interacted with microfibers before and not even realized it. When, for example, cleaning the lint filter on your dryer, those are microplastics. Now, if some of you are skeptical about your clothes being made of plastics, first of all, I am not referring to this. Most of our clothes are made of plastic in some way, including nylon, for instance. For a long while, polyester has been the leader in clothes production, and polyester is a plastic, the most common variety of which is used to make PET, which is used to make water bottles. Another example of microfibers in our clothes is this image of a pair of stretch jeans that have been composted for more than a year. And as you can see, all the plastic fibers remained, while the natural ones that could break down have broken down. I also want to caution you away from viewing biodegradable plastics as the current solution. So while not all biodegradables are bad, there's a spectrum of biodegradation. And as with all new technologies, there are growing pains to fully figuring it out. And so in theory, the idea is great, plastic that will magically disappear from the environment. Unfortunately, the term biodegradable is used for a lot of things. It's not well defined and it's not well regulated. So many assume that it means that the product is either made from green sources or will break down entirely in the environment, when neither of those are possibly true. In fact, Australia is soon banning biodegradable plastics because of this confusion. And so an example of this is this compostable cup. So it's got the green label on it. It says it was made from renewable resources, and it says compostable on it. But unfortunately, a lot of products like these won't break down in your backyard composting bin. They need to be broken down in an industrial composting facility. And in the regular environment, they will behave as regular plastics do. Additionally, a biodegradable plastic bag came out recently that it turns out didn't break down, it fragmented, forming microplastics. And additionally, biodegradable plastics, this trend is making the idea of single-use plastics okay again, which is just not the direction that we need to be going in right now. So I want to make a distinction that's really clear. So first of all, you can have bio-based plastics, which are those that are made from non-fossil fuel sources, like algae or starch or some other technologies that are coming out. But just because a plastic is bio-based or made from green sources does not necessarily mean that it's biodegradable or that it will break down entirely in the environment. In the same vein, biodegradable plastics aren't necessarily green-based. You can have petroleum-based biodegradable plastics. And additionally, there's the confusion on what the term biodegradable actually means, on whether it means actually breaking down in the environment or not. And so the needle that we need to be threading here is this little sliver in the middle, where we're producing things from green sources to reduce fossil fuel dependency, as well as for them to be biodegradable, actually biodegradable, and to fully break down in the environment. Now, finally, one thing that we love to do with VIMS is a cleanup. So even if you aren't near the water, remember that mismanaged waste leads to the ocean. For example, plastic in the street that may be washed into a storm drain, for instance. So picking up the couple pieces of trash that you see on the side of the road during a walk, or bringing a trash bag to the park or beach when you opt outside are great ways to approach this. And when you clean up, you can actually help contribute to plastic science as well to help us understand how plastic debris travels and where to focus conservation efforts. Using this app is called CleanSwell and was made by the Ocean Conservancy. And in it, you can record the types of debris that you pick up and how many of each type you've picked up. Science is fun, guys. I also wanted to highlight this local business in Williamsburg. If you aren't local, I encourage you to search out places like this in your area. It's a shop called Feel Happy in the Williamsburg outlets. And they sell non-plastic products from body lotion and sunscreen, dog shampoo, as well as cleaners and candles, Swedish dishcloths, which are reusable paper towels, and crayons. Additionally, they have a refill bar that can even be done by delivery. So I've included the link to their website at the bottom of this slide for you to look more into if you're interested. And this is one way that you can use your voice by using your wallet. So shop in places that have reduced their plastics footprint, and where you can, stop buying plastic products. And if enough of us stop buying, they will stop producing those products because they no longer make the company money. So it's important to remember that no one can do everything, but that everyone can do something. We don't need a few people being absolutely perfect and not using any plastic whatsoever. We need millions being imperfect, but decreasing their plastic use where they can. And again, the emphasis should be international government regulations as well as changes to plastic industry. So just choose the few ways that work for you to help address this issue and let yourself go on the rest. If you can, even get involved to help address this issue in policy. And this is one thing that was emphasized in this figure from a microplastics review paper that my research advisor, Rob Hale, as well as my fellow grad student, Meredith Evans Seeley, published last year. The review discusses global scientific and public and policy challenges towards stopping microplastic pollution. And a lot of these are to help inform and direct the huge amount of global microplastics research going on. But what I want you to walk away from this slide with is that microplastic pollution is a global issue that will require international cooperation to solve. To understand the capabilities and especially the pitfalls of green chemistry, like what I discussed about depending on bioremediation as the solve-all until the technology has developed more. And finally, that it's important and should be the biggest focus to implement policy to mitigate plastic pollution. And with that, here's my contact info, both email and Twitter. Microplastics Science Twitter is very active, so come say hi. please feel free to reach out with any questions that you have for me. So thank you so much for being with me here today to celebrate World Oceans Day, and I'm excited to answer any questions that you may have for me.